We're back here talking about parametrics, and this is the third video in the series on 10.1, and we're going to talk here about Arclength. So I'm going to review and refresh your memory a little bit on Arclength when we were talking about rectangulars. If you remember, when we have any curve, we took a little piece of the curve, a little differential strip there, and we could say then, using a little bit of Pythagorean theorem, that that little delta s, the little bit of that arc length, would be, just from Pythagorean theorem, would be a delta x squared plus a delta y squared, and then we'll take the square root of it to get that little bit of length right there. Then we did this kind of little game where we said we're going to multiply by 1 in the form of delta x over delta x, and we then brought the denominator delta x inside the radical, and to do that it had to become squared, and so we got delta x squared over delta x squared plus delta y squared over delta x squared, and we left that other delta x that was in the numerator on the outside. That then became, so the delta x squared over delta x squared is just 1, and we said that delta y squared over delta x squared, we went through a little bit using the mean value theorem, but eventually we said that was really going to be f prime of x squared, and then we had our delta x on the outside. That was just our little differential length, and so from that we got our formula for the arc length in rectangulars was going to be an integral, and it would go from, okay, I think I'm back here. I'm bumping things that I didn't want to. So we're going to get our integral that is going to go, so we're going to integrate this from some x value. I can get my pen back up here. From some x value to some other x value, and that is how we will get the arc length in rectangular form. Now, to do this in polar form, or I'm sorry, parametric form, we start with the same idea, that our little straight line segment there is going to be approximately the square root of delta x squared plus delta y squared. This time, instead of multiplying top and bottom by 1 in the form of delta x, we're going to multiply by delta t over delta t. So then what we will do is we'll bring the delta t in the denominator inside, and so we will get the square root of delta x squared over delta t squared plus delta y squared over delta t squared, and then we'll still have the other delta t that was in the numerator still left on the outside. So that then is going to become, once we do this, the whole kind of mean value theorem like we talked about with rectangular, that's going to become, inside our radical, it's going to be a dx dt squared plus a dy dt squared. And we've got that delta t still on the outside of the radical. So the entire arc length then becomes an integral, and we go from some t value to another t value, as long as the curve doesn't overlap or cross over itself. So you have to be a little careful of that when we're in parametrics. And then we're going to get that the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and that delta t becomes a dt. So that is our formula for arc length in parametric form. So let's see how that is actually going to work in practice. So I'm going to change screens here, and let's pick an example. So we're going to take a look at what's called an asteroid, not an asteroid, but an asteroid. So this is a parametric shape, and so it's given by the parametric equations. X is going to equal 2 cosine cubed t, and y will equal 2 sine cubed t. And you can graph this on your calculator, and you can choose the t values to go from 0 to 2 pi, and you can choose your x values, your x min and x max on your calculator to go from -3 to +3, and the y values to go from -2 to +2. And so when you graph that, what you're going to get is something that looks sort of like this. So there's our axis, and our shape is going to go something that looks sort of like this, hopefully. And that's what is called an asteroid. So our challenge is going to be, can we find the length of that asteroid? So find the length as if you walked all the way around, starting at one place, all the way around until you got back to the place where you started. Let's say find the length of the asteroid. So what we're going to do is, first of all, to make things simpler, because of the symmetry, we know that the length in quadrant 1, if we multiply that by 4, it will give us the whole thing. So we're just going to find the length of the piece that's in quadrant 1 and then multiply that by 4. Find the arc length. We're going to say in quadrant 1, and then multiply by 4 to get the length of the whole figure. So in our formula, we know that we're going to need to know first what is dx dt, and then we're going to have to square that, and then we're going to have to find dy dt and then square that. So it's going to get a little messy here. Dx dt is a chain rule derivative, so we're going to bring that 3 out in front from the cosine cubed times the 2 that's already there. We'll get cosine to the second, and then we'll multiply that by the derivative of cosine, which is going to be a negative sine of t. So I'm going to clean that up a little bit and call that a -6, I guess, cosine squared of t sine of t. So that's dx dt. Now dy dt in a similar fashion is going to be a chain rule derivative, so we'll go 3 times the 2 sine to the second, and then times the derivative of sine, which is cosine of t. And so again, cleaning that up a little bit, is going to be 6 sine squared t cosine t. Now from there, we're going to have to square that. So we need to find what is dx dt squared. So when we square that, we're going to get that -6 squared is going to become 36. The cosine squared is going to get squared and become cosine to the 4th. The sine will get squared and become sine squared of t. So there is our dx dt squared. We also need dy dt squared, and so likewise we're going to get a 36 sine to the 4th t cosine squared t. It's starting to look like a mess, but this is actually one of very few arc length problems that we're going to be able to do without using a calculator. I know you're very happy about that. So to find our arc length, we're going to do the integral, and to get quadrant 1, we want the t values to go from 0 to pi over 2, and we're going to go we're going to go 4 times that, because we want to take the arc length in quadrant 1 and multiply that by 4. Now we're going to take the square root of, we have our dx dt squared, which is 36 cosine to the fourth of t sine to the second of t plus 36 sine to the fourth t cosine squared t and a dt. Now when you look at the inside of that radical, you can see there's all kinds of things that we can factor out. And so what we're going to do, still inside the radical, so we have 4 integral 0 to pi over 2. Now still in the radical for now, but we have a common factor of 36 and a cosine squared and a sine squared. So that's 36 cosine squared t sine squared t. That will leave inside that radical, I guess, a cosine squared t plus sine squared t. And then we have the dt. So we can see, conveniently enough, that sine squared plus cosine squared is our favorite trig identity. That's just 1. That's leaving us with the square root of these things that are perfect squares. And so what we get then is that we're going to get 4, and we still have that integral from 0 to pi over 2, but the square root of 36 is 6. The square root of cosine squared would technically be the absolute value of cosine, and likewise the square root of sine squared would technically be the absolute value of sine of t, but we're just going to be in quadrant 1, and sine and cosine are always positive in quadrant 1, so we can get away without putting the absolute value in there. Okay, now we're moving along. We see we can actually do this integral by hand. Let's say maybe u is sine of t, then du is going to be just cosine t dt, and so the dt is going to be du over cosine of t. And so our integral is going to become, I'm going to leave off the limits right now. Actually, should we change them? We can do that. Let's change those limits and make them u limits. So we can see u of 0 is going to be the sine of 0, which is 0. That's going to make that lower limit be 0. And we know that u of pi over 2 is going to be the sine of pi over 2, which is just 1. So we can make our u substitution and use our new u limits. So that means we're going to get, we have that 6, and then we've got the sine of t is going to be u, and the du, the dt, the du over cosine t will cancel that other, and this is going to be our integral. We can then say that if we pull the 6 out, we have 24 times, and then the integral of u is going to be 1/2 u squared. We can cancel the 1/2 with the 24 and get 12 u squared. We're going to evaluate that from 0 to 1, and that's going to be just 12. Wow, amazing that something this complicated had such a very nice arc length. All right, very good.